Hello, my name is José Felipe and I'm going to present my work that is heat transfer analysis of a solid propellant rocket combustion chamber. The combustion chamber is a cylindrical tube charged with the propellant that is consumed during the combustion process. According to Sutton and Bublers, about 5% of the heat generated is converted into thermal energy for the material, and the rest in kinetic energy in the nozzle. The study of heat transfer is extremely important to choose the most efficient materials for the project. And besides that, most of the studies are based on inverse problems with experimental data to obtain the heat flux. The figure below shows the heat transfer process in the combustion chamber. So this is the combustion chamber here outside. Inside is the propellant, and this is the heat flux caused by the combustion of the propellant. Okay, so the main objective of this work is obtain the temperature profile of the combustion chamber propellant without the need of experimental data, consider the moving boundary of the propellant in a mathematical model. So I'm going to consider the consumption of the propellant during the combustion process, and the domain is going to vary over the time because of that. And the methodology is the generalized integral transform technique. The propellant will consist of a homogeneous mixture of sorbitol fuel and the oxidant, which is the potassium nitrate. And the combustion reaction of the propellant will take place in approximately 4 seconds, and the chemical reaction of the combustion process is given by this reaction here, the reaction below. The heat of the combustion can be calculated by the difference in the enthalpies of the products and the reactants of the chemical reaction, where N is the number of moles of the molecule, AF is the enthalpy of formation, which is related to the chemical bonds, delta AS is the difference in sensitive enthalpy, which is related to the combustion temperature. The combustion chamber and the propellant have a cylindrical geometry, so I'm going to consider the heat conduction equation in the cylindrical form, with the following boundary and initial conditions, where inside I'm going to consider a heat flux caused by the combustion of the propellant, outside I'm going to consider that is insulated, and the initial temperature is the environmental temperature, where K is the heat conductivity, which are varying over the domain. The first one is about the propellant heat conductivity, and the second one is the heat conductivity of the combustion chamber. And this is the same idea in the density and in the specific heat. The illustration here actually is a video showing how the propellant is consumed during the combustion chamber, and we can see how the domain is varying over the time. First, I'm going to add a filter to make the boundary conditions of the heat conductions equation that I showed before homogeneous. So this is the heat conduction after applying the filter. This is the new boundary and initial conditions, where this is the definition of the temperature with the filtered temperature and the filter, the definition of the filter, and this is the heat flux, where Q is the heat combustion, T is the time of the combustion, which is 4 seconds, and A is the surface area of the propellant. The first step to start the generalized integral transform technique is to define the transformation pair, where this is the transform and this is the inverse term. Psi is the solution of the Sturm-Liouville problem for Cartesian coordinates in a moving boundary, and the solution of the n function, n values, and the norm are given by those terms here. The future equation of the problem is This is the equation that I showed before, after applying the filter in the heat conduction equation. The coupled ODE system is obtained after multiply both sides of this equation by RC and integrating over the domain RA and RC. And this is the coupled ODE, and this is the initial condition, and this is the definition of those terms here. And all of those terms are solved analytically. Okay. The problem consists of a 1 meter long cylindrical tube of aluminum containing a propellant of the same shape inside. Table 1 and 2 shows the physical properties of the propellant and the combustion chamber respectively. And A react corresponds to the total enthalpy of the reactants and will be used to estimate the heat transferred to the combustion chamber. Table 3 shows the heat combustions for different temperature obtained through the chemical reaction and the heat combustion equation. The values of enthalpies were obtained through the Nist-Janaf thermochemical tables for each element of the chemical reaction. And we can note that in 1600 the heat approaches to zero, and that's approximately the adiabatic temperature flame. And after that the chemical reaction will become endothermic, and that's not the case of the problem, because it's exothermic. The results were obtained using the Wolfram mathematical software. In order to solve the system of differential equations 11a, the end-the-solve routine of the software was used. Figure 3 and 4 shows the temperature distribution. Consider 5 and 10% of the propellant A react with a truncation of 100. Both graphics are basically the same, however the first one receives less heat than the other. Each line represents the temperature distribution for the specific step of time, and in the left side of each line represents the moving boundary that is growing up over the time. And in the right side we can see the temperature of the combustion chamber that is growing. The temperature is growing up slowly because the propellant is insulating it's protecting the combustion chamber. The figure below corresponds to the logarithmic graph of the error presented in the equation below at different points on the cylinder. So this is the equation of the error, and this is basically the convergence of the problem. And the red dots are the moving boundary, it's the convergence on the moving boundary. The green dots are the convergence of the RB, and the purple dots are the convergence of RC. It can be concluded that the moving point RA decreases its temperature with time. That happens because the moving boundary is consumed before the heat comes to a deeper layer of the propellant. The insulating characteristic of the propellant thermally protects the engine until the end of its consumption. However, this doesn't occur in practice because the propellant is also consumed in the axial direction. For a moving boundary, choosing an eigenvalue problem in Cartesian coordinates, even if my model is in cylindrical coordinates, is extremely efficient because we work with trigonometric functions, and it's pretty much easier to work with, and the convergence was not affected. For future work, one can involve this study with more precise considerations. One of them is to seek alternatives to obtain the heat released during the combustion process. The second would be to develop a mathematical model that also considers the temperature distribution in the axial direction. So I finished my presentation. Here is our emails for contact for any questions. And thank you very much for your attention.